Hello, this is Dwight Goins and Tiying, and we did our presentation, gp1, on location-aware multi-drone networking with intelligent packet forwarding. In today's talk, we are going to talk through theory and implementation. Ting is going to present the problem statement, talk about the motivation, and give a quick overview of Q-learning, the Markov decision process, and the Bellman equation, and explain how our algorithm follows the Q-learning algorithm and the benefits of how solving using the Q-learning solves our problem. I will then talk about implementation and go into source code and talk about how we, number one, did the detailed design of implementing the Q-learning algorithm, how we created the UAV environment, and show you a demo, an example of the Jupyter Notebook running, and talk about future work on what we could do to better enhance this presentation. Thank you.
Hi, this is gp1 presentation 2. Our research paper named the location where multi-drone networking with intelligent packet forwarding. I'm Tiying. Let me introduce my part, algorithms model details. I will discuss our approach to enhance UAV routing protocols in past disaster communication environments using Q-learning. This presentation will focus on the challenge UAV networks face and how Q-learning offers a solution for optimized routing in the dynamic resource constraint settings. Okay, the first part will let me discuss of the problems statement. In the past desired environment, UAVs operate in highly dynamic networks where connectivity is isolated due to the node mobilities and the environmental factors. The main challenge we face in UAV networks, especially in past disaster scenarios, turnaround dynamic change in connectivities, unreliable links, and high mobilities of UAVs. Traditional routing protocols will addressing some of these issues, often result in delays and increased overhead. The reliance on ferrying UAVs and for the data transfer is resource intensive and in lower density networks. This is a higher chance for the data loss. And this challenge motivates us to explore how approach to make UAV routing more efficient. So what is our motivation? So our work is inspired by the LADTR protocols, which is efficient in many cases, but also present limitation. LADTR offers a strong solution by predict the UAV locations and using varying UAVs to transport data. However, the limitation become apparent in dynamic environments. Frequent location queries lead to delays, and the GPS data can be unreliable in certain conditions. Additionally, the rely on the ferrying UAVs introduced significant overhead, and a single copy forwarding poses the risk of the data loss. Next, what is the Q-learning? Q-learning is a model-free reinforcement learning algorithm that allows a agent in our case UAVs to learn the optimal strategies through test and error. So the Q-learning offers a mobile solution to the routing problems in UAV networks by allowing the UAV to learn from their environments. Through repeat the interactions, UAV learn which actions lead to successful data transmission. This reduces the need for the frequent location queries and minimizes the reliance on the foreign UAVs. Over time, the network becomes more adaptable to change, improving the overall efficiency. So the next is the UAV routing problem is modeled as a macro decision process, MDP, where each UAV acts as an agent interacting with the environment. The state space includes the UAV's position, link quality, and the status of the neighbor's UAVs. The action space include decisions such as forwarding data to other UAV or storing it for the future transmission. In order to apply in Q learning, we need to model the problems as a macro decision process. The UAV's current position, neighbors, and the state of the network present the state space. Each action, such as forwarding or storing data, impact the rewards which successful transmission and kinetic features. So the transitions functions act for the unpredictable nature of the UAV mobilities. So we use the Q-learning algorithm. The Q-learning algorithm is structured as a loop where the UAV continually notice its environment, make decisions, and learn from the outcomes. Through the exploration of the UAV improves its ability to make optimal decisions, eventually learning the best route for the data transmission in dynamic environments. The Bayerman equation is the central to the Q-learning, as it has helped the UAV update its understanding of which actions are the best. It does by balance the immediately rewards by the future expect the rewards, ensuring that the UAV makes decisions that will be benefit both short-term and long-term performance. This algorithm pseudocode explains the Q-learning algorithm we used for optimized UAV routings. So it shows how the UAV continues updates its knowledge of the best actions to take in different states, learning the optimal policy for the data forwarding. Okay, the primary benefit of applying the Q-learning to UAV networks is that the significant reduce the reliance on the foreign UAVs by making decisions autonomously. UAV can dynamic adapt to changing conditions, improving the overall network performance. So in conclusion, Q-learning provides efficient and adaptivity solution to the challenge faced by the UAV network in the past disaster scenarios by improving the decision-making and reduce overhead. This approach ensures that UAV can deliver data reliability even in the high dynamic environments. Okay, thank you.
Hello, I'm Dwight, and I'm with Tiying, and we are gp1, and I will be talking through the source code implementation of the location-aware drone network. Okay. So first thing I want to talk through is a little bit about the difference between a single drone network and a multi-drone network. A single drone network is something where you have a single drone that's out flying about taking pictures, and usually what the single drone network, what that does is that may be fitted with a mobile device or some type of Wi-Fi or Bluetooth connectivity sensor or mechanism on the drone that allows you to connect to some wireless network. In the case of a single drone, it typically can send data and receive data. It's typically designed for one purpose and one main job and a very specific task for a very specific network. Now, when that drone flies too far, it gets out of range of the wireless network, and that's when you start to see the problems that we have. And so there's no redundancy. There's no way to dynamically change the behavior of the single drone. Single drone just goes out, captures the data, and comes back and forwards it to the ground station. Or while it's live and it's connected, it just hovers in a certain area, captures the data, and then, when that network is no longer available, that's it, and it's done. In a multi-drone network, in a multi-UAV scenario, this is one where we can have different drones performing different tasks based off of the need at hand. So, for example, you can have 4 or 5 drones that are out there that are searching and doing a search and rescue operation, capturing video and audio feeds and streaming that data. And then you have some of the drones out of a 10 set of fleet. You can have some of the drones, maybe 4 drones or 3 drones, that are acting as a proxy or ferry. And those drones are just there to fly along and tag along with the main searching drones in order to keep the connectivity alive, in order to send the data to the ground station or to some ground van or vehicle or whatever the network is connected to. So what we thought of doing is, wouldn't it be great with this fleet of drones if the drones had enough smarts on them to determine when would be best in order for it to be a ferry drone versus a searching drone? And that is, in essence, what we have built out in our code today. So again, the main goal here was to figure out a way to have these fleet of UAVs determine what their role and behavior was going to be based off of network conditions. And the 2 main roles that we're talking through here is a searching role and a ferrying role. Searching meaning it's going out and performing some task, doing a search and rescue, it's connecting to some video feed or audio feed, and it's doing a very pinpointed particular task. Ferrying drone, on the other hand, is just meant to be there as a network drone. It's meant to be there to extend the network to the reach of that searching drone while keeping connectivity to the ground station. So the way in which we can do that, we first had to create and simulate a UAV fleet network environment. And so we decided to do that by creating a kind of like a 1-by-1 grid, but we'll talk about the environment in a second. But just create a grid and stick some drones up there randomly and randomly make them search drones and ferrying drones, and then watch the behavior of them. The other thing we wanted to pay attention to was the position and velocity. Obviously, when a searching drone gets too far, it gets out of reach of the network range. And the network condition may be bad, the throughput may be bad, the round trip time may be too long, and all of that may cause the searching drone to start dropping packets and start dropping the media and the data that it's capturing. So over time, we wanted to understand how that might work. The other thing is, drones, when they're flying, they have velocity, they have direction and magnitude and where they're going and how fast they're going. So we needed to keep track of that to see maybe that might be causing issues in the networking conditions. And we wanted to figure out, with all of this information, with the network conditions, with the position of the other neighbors, of the other drones, the position of the ground station, all of those having flying options, then could Q-learning be used as a reinforcement learning model or algorithm in order to help us determine when would it be best for a searching drone to turn to a ferry drone and a ferry drone to turn into a searching drone over the network. So we did that through reward functions. All right, let me bounce over into a demo of the app. So here's the location-aware multi-drone collab Jupyter Notebook here. And again, with the link that's in the slide, you have access to this. And the first thing we talk about is what the key objectives are and the description of what we're trying to do. So here you can see we've imported some packages, and these are just some Python packages that are running for this particular connected node. And here we're connecting to Google Drive so that we can kind of save like the animated images off and load them up later. So that's just asking me to connect to my Google Drive here and mount the Google Drive. So here's popping up my Google Drive here, and if you want to use this with your Google Drive, you just have to change the location. I have a drones folder in my Google Drive, so you just need to change the location of where you want the files to be uploaded. So I'm mounted to my Google Drive. Here I explain about the UAV routing problem as a Markov decision process, and we talk about the agents, we talk about the state space, and in the state space these are the parameters or the attributes that we're paying attention to: position, velocity, network condition, buffer status, round trip time, the good put, the role, the ground station position, and just the name status. So if we know that, are we receiving data, have we forwarded the data, things of that nature, right? Just the name state of what all of these values mean. And then here we have a state class that keeps track of those parameters. Okay, so this is a Python class that maintains the state. And what we're going to do is we're going to initialize a grid that looks something similar to this. And what the circles mean is the most inner circle is going to represent the network condition. The next is going to represent the good put, and the next one is going to represent the round trip time. So we have 3 circles here that represent the different conditions and environments that this one particular drone is working with. And the big gray area is kind of like the network range that this particular drone represents. Okay. For our actions, we're going to have these 4 basic actions. Basically, the action is going to be, are we switching to a ferry, or are we switching to a search? Are we forwarding the data, or are we receiving and staying? And if we stay too long, we may risk losing the data, right? The data packets may drop, right? So those are the 4 actions that we're going to use. And then based off of those actions, we'll have different rewards. So for example, if the data is forwarded, we'll give a reward of plus 20. If it's forwarded to the ground station, we'll give a reward of 100, because that is the main goal. That's what we're trying to do, forward data to the ground station. If the data is dropped because we're staying and there's nothing for us to forward and we can't connect, we're going to do a minus 20. A minus 20. And if we get a round trip time that's like a timeout and everything is really going haywire, we'll do a minus 100, because we want to always make sure we're in some type of connectivity after so many seconds. Okay. So this is based off of the ladder document. The ladder document gave us this map here that just kind of showed how they could use these different drones to help with the network. But these drones were basically designed. They weren't using any learning-based approach to determine the searching drone versus the ferry drone. Our document is all about how do you use Q-learning to turn these yellows into greens randomly at runtime, while still connecting to the ground station down here. All right, so here we have the UAV environment class. This class is going to be a class that has a method called reset states and reset. What reset states does is for every UAV, each UAV has its own network condition. So we randomize the network condition for each UAV, and that's what reset states does. And reset just basically resets the position of the drone whenever we run through our different episodes. We also have a step function that allows us to check what current action we're in and move to the next action based off of the previous action. So in this case, for example, if we are on a switch to UAV action, then we may, depending on what's happening, we need to perform this action of taking the role and changing it from 0 to 1. If we're on the switch to survey, we need to take the role and switch it from 1 to 0. If the action is stay, which is 3, then we go ahead and check the round trip time. If it's greater than 120 seconds, then we drop the data because we can't stay any longer. Otherwise, we're stay. That means we're receiving data. So we're naming the state receiving the data. If it is forwarding the data, we have 2 options. Either we could forward to the ground station or we could forward to another ferry. And so here we're just basically saying, yay, we forwarded the data. And then we're checking the velocity and position. and basically setting up the rewards based off of that. But here we could have wrote a little bit more code to determine if it was forwarded to a ground station or forwarded to a ferry, and add different rewards from that. And so what you'll see here is the rewards are calculated through the reward function, which is where we do that check. So in the reward function, we have we're checking the name of the state. So if this was a dropped, we set the reward to -20, like I mentioned earlier. If the round trip total round trip time was less than 5 seconds, then we give +15 as a reward. Otherwise, we give -10 as a reward. If the good put value is, let's say, greater than 50 megabytes per second, we give +15. Otherwise, we subtract. If we have a buffer, if we have 25% of, if we have over 25% of our buffer left, then we'll give a reward of +5. Otherwise, if we don't, that means we're less than 25% of data we can hold. We'll go ahead and subtract. If we're in a forwarding status, we're ready to move the data now to either a ferry or ground station, we'll check. We'll first start and say, yeah, we're forwarding data. We're in a good network. Everything is good. So we'll set the reward of +20. Then the next thing we'll check is that how close are we to the ground station? How close is any one of the UAVs to the ground station? Because if it's a searching UAV, they can just directly communicate to the ground station. If it's a ferry UAV, they can communicate to the ground station as well. So depending, how close are we to the ground station? If we are very close, if we're within the same region, which is what the 0.2 means, then that's a good thing. And we'll go ahead and reward it 100 because they were saying we've met our goal, right? That's the whole purpose of this. Otherwise, we're receiving data. That means we're pretty much staying put. Everything is good. So we'll receive a reward of +10. But if we stay too long, then we go ahead and subtract 100, okay? And then last but not least, this is our done condition that checks for when we are finished with our checking condition. All right. So then, I think I ran that, right? Sorry about this. Yep, I'll run it again. All right, next we have our Q-Learning agent. Our Q-Learning agent does all the hard work for the most part. We initialize all the environment settings, we choose actions, we learn, we continue learning, we get the current state, and we extract the policy once we're done with a particular episode to find out how well we did. Okay, and then the training function is the function that keeps looping over and over and going through a number of different episodes in order to get the best optimal policy based off of the best stated reward. Okay, so that sets up the training, and then underneath that, if I scroll down, sorry, this is where we actually run it. We could run 35 episodes with 10 UAVs and give a maximum number of steps. For the purposes of time, I'll set this to something quick. I'll just say 50, and I'll say we'll have a very small number of episodes. We'll just say 5, just for the demo to show you how this works. So I'll run it, and you see here that we randomly created a set of UAV states in the network. We have some searching drones here with some good networks. We have some UAV 5, looks like it has a bad network condition with the red, and an okay good put with the yellow. We have UAV 6, started moving here. UAV 6, we see the ground has this big, ground station has this big gray area here with connectivity, right? And we see UAVs all around. And then what you'll notice here is that these UAVs, after they run through the policy, the UAV 5, where it's up here now, moved over into this quadrant, and it went from being a searching UAV to a ferry UAV, right? See, it changed to the red color down here at the bottom, okay? And then you can kind of see the animation of what's happening here. Here, you can also see the vectors. That's what these little lines represent, the vectors of which direction these UAVs are moving. And I think this is the movement. Yeah, so here you see some of these moving around to get into better position utilizing Q-Learning. And you see in this particular case, it's swapping back and forth between different roles based off of who it's trying to communicate with. You can see the Q table here and the V tables. Okay, that is all for the code implementation. Thank you. Hello, this is Dwight Goins and Tiying, and we did our presentation, gp1, on location-aware multi-drone networking with intelligent packet forwarding. In today's talk, we are going to talk through theory and implementation. Tiying is going to present the problem statement, talk about the motivation, and give a quick overview of Q-learning, the Markov decision process, and the Bellman equation, and explain how our algorithm follows the Q-learning algorithm and the benefits of how using the Q-learning solves our problem. I will then talk about implementation and go into source code and talk about how we, number one, did the detailed design of implementing the Q-learning algorithm, how we created the UAV environment, and show you a demo, an example of the Jupyter Notebook running, and talk about future work on what we could do to better enhance this presentation. Thank you.